Okay, so the first speaker is an extraordinary economist. I would say young economist, but that just shows my age rather than Sendhil. And Sendhil Mullainathan has worked on such a diverse set of economic problems and issues, and in each place he writes a seminal paper and then goes on to do some more things in that area, but it's very rare when somebody writes a seminal paper in behavioral economics, a seminal paper looking at CEO pay in a critical area, a seminal paper, etc. So, and he told me he just comes from giving lectures on the use of machine learning in economics. And it's also an interesting aspect, both of him and of the way science is being done today. If you look at the names of the people, they're on his co-authors. They're not all economists by far. They come from different ethnicities, different universities, different places, and that shows the way I think people connect nowadays in the modern world. I was very lucky. Sendhil took my labor course X years ago and was one of the most brilliant and creative people in that area, and that's not even his specialty. So Sendhil, you come and you're on.
Thanks, Richard, for the generous introduction. I'm just going to dive in, and thank you all for coming out on a Monday morning on one of the last weeks of summer at 9 a.m. I could like to say I'm going to be competitive with being on the beach, but I'm pretty sure that's not true. So let me just start with a bit about myself. Here's a kind of problem from labor economics of which Richard is a master. This is the unemployment rate amongst blacks and whites in the United States. What's shocking in this graph is how much more likely African Americans are to be unemployed than whites. This gap is persistent. You might have open the newspaper and you'll see things like Ferguson. Even if we don't get to murders and violence, there's sort of an ongoing racial gap in nearly every domain. Employment is one of the biggest domains where we see a massive racial gap. And so you might see a graph like this, and I see a graph like this, and I want to know what's going on. So I want to just give you, not by way of anything I'm going to talk today, but a brief understanding of the way I might have thought about things like this in the past. So a co-author of mine, Marianne Bertrand, and I see things like this, and we say, well, what can we add to this discussion? Of course, one of the key questions you'd like to understand from a graph like this is how much of this has to do with African Americanness, and how much of it has to do with the fact that African Americans are simply in a certain place and time, have certain skill sets and other skill sets. So to answer that type of question, we took a resume like this and simply just made 2 copies of it and simply randomized the name on the resume to this name or this name. Now the name on the left is a white name and the name on the right is an African American name. And we simply sent these out to thousands of employers, and what we found was a very big gap, that the same resume elicits a huge difference in response rates, about 50% more responses if it has a white name on it. So that's about, for every 2 job interviews that a white person gets, so the African American person gets, the white person gets 3. This is a huge gap. I'm telling you this just so you can get a sense of where I'm coming from. This is probably how I would have analyzed most questions. I would have tried to understand the element of it that was inherently causally important and tried to come up with an empirical strategy, this is one of them, to get at that causally important element. And there is a hubris amongst economists. I think you probably would agree with this, Richard. And like all people, I have my own hubris. And that hubris is, when it comes to empirical work, we're the best social scientists. And that hubris has kind of been built into us for the last 30 years. I think that it happens. Then you turn to things like this. This is just one example. This is a paper from a face recognition data set. And you read a paper like this and you go, what do you mean they take all of these faces, take this in as data, and are able to come up with a face recognizer? How would you even do that empirically? And you start to pause and say, there's no way I would know how to do that. That is well beyond my skill set. How can I be a good empiricist if I have no clue how to do this activity? And it's not just one thing. It's not just a face recognition data set. It is really the vast majority of things you encounter when you leave a little world of economics. It's everything from natural language processing to prediction tasks, even in credit markets, which you think is something that we as economists ought to do. No one is going to go to an economist and say, you're the person I would like to build a credit score model to. My students wouldn't build a good credit score model at all. They'd be just dreadful at this activity. So this is an interesting wedge where suddenly I found myself in this position where it was pretty clear there was something here that was beyond my ability and that I wanted to kind of understand. So of course, as an economist, the first thing I thought was arbitrage. This is a finance term, and those of you who don't know what arbitrage is, it's summarized by this picture, I think. You can take a moment to understand it. And perhaps a better way to label this picture was, you're all looking at this, and I'm thinking, this is orange juices are selling for $4 in the world of machine learning, and they're selling at $5 in the world of social science. One of my co-authors said it really should be this, but I don't know if that's true. And so this is the wedge that you sort of think to yourself, oh, wow, these empirical tools could really enrich and enliven what is essentially an empirical science. The problem you encounter, of course, is the problem that these tools are amazing, but they have an Achilles heel. An Achilles heel that is so fundamental, you ask yourself, gee, is this surmountable? And perhaps the Achilles heel is summarizable with this XKCD cartoon, which you can read at your leisure. But for those of you who work in this area, it should be pretty straightforward what the Achilles heel is. It's the bugaboo of causation versus correlation. These tools are fabulous for unearthing causation, for correlation. They'd be great if they were unearthed. But they don't give us any guarantees causally. And causality, as you saw in the first example I told you, is what we spend all our time struggling with. We spend all our time struggling with the question of, is African American versus white? So now you're left with a tension. And you say, causality really is central to what we do. And it's central to what we do because much empirical work basically tries to improve policies, if you just boil it down. And if you think of the policy decision, the nature of the information we need to make that decision seems inherently causal. What do I mean by that? Most often we're struggling with, should we do policy X? And that question of should we do policy X is tied intimately to the question of what will policy X do? Which of course is tied to the question of what happens with and without X, which is inherently about causality. So that left me with a long way of saying, where am I coming from? About a year or 2 years ago, we were left with this conundrum. How can sort of machine learning high-dimensional data analysis be useful to us, given this is what we're struggling with? Now, what I'm going to tell you is, in fact, I think it's immensely useful. I think it's wrong to set up this, this wedge. I think it's an entirely fictitious wedge, but I think it is a wedge that's natural given where I was coming from. So I want to tell you why I think it's fictitious. To understand the fictitious nature of it, or rather it's not fictitious, it's overblown, I want to talk you through two toy policy decisions. The first one, imagine you're the head of a country that is suffering, or a county, whatever, that is suffering from a drought, and somebody comes to you and says, you know, I can help you with your drought. I can do a rain dance, and it will increase the amount of rain in the area. So that's one policy decision, pretty important policy decision. Here's another policy decision. You're thinking of deciding whether to go to work today or come to this conference today, and you were deciding whether to bring an umbrella to work. Two decisions. Now, these decisions have very large numbers of shared common elements. To the extent that they are, first, they're decisions. That's the important thing. So as I said, if we're trying to inform policy, we have to think about the decision part. But second, they both rely on data of the type Y variable rain, X variable a bunch of stuff that might help in that. And both of them would like to estimate a function of these X variables that is of rain. The key distinction is, what is the property of that function that we would like? In the rain dance case, we would like assurances about causation. And in the umbrella case, we merely want a good predictor. What do I mean by this? In the rain dance case, I would like that the beta coefficients that I get on rain dance are causal, and that if I were to change rain dance, I actually learn what is going to happen to rain. In the prediction thing, there's no sense in which I think that changing whether I take an umbrella to work or not, I mean, it may feel like that some days, but your decision to take an umbrella, that much I'm pretty sure I can guarantee you, is unrelated to your decision, to the outcome. So how do we think about this? What I want to try and convince you today is that the type of things that I and others have been spending their time doing is focusing on, I don't know what happened, there we go, is focusing on rain dances in the world, but in fact, there are many umbrellas in the social science world. And I want to convince you that this is a meaningful exercise by walking through one example carefully. Before doing that, let me give you a way to kind of, at least I've come to understand the nature of prediction versus causation, drawing on the sort of graphical models framework that people have so wonderfully built over the last 20 years. So to do that, it's going to be a simple framework, but it proved illuminating for me. So here's a simple graphical model where there's sort of x variables, there's a y variable, and then that in turn generates some payoffs. Now, in the example I gave, the y variable is rain. The x variable could be various atmospheric conditions and other things. There is a decision to be made, and the entire distinction between prediction and causation has to do with where we draw the next arrow. So if the decision to be made simply feeds into rain, then we are in a causal world, because the decision is upstream from the y variable, and that decision is going to affect the estimator. If the decision is downstream, that is, it affects payoffs, but there's an exclusion restriction that it doesn't affect y, we are in a prediction world. Viewed in this light, prediction and causation are shockingly similar activities, and it's hard to believe that there aren't many policy decisions where you would draw the arrow down and not draw the arrow up. You can also see the extent to which prediction and causation are merely just exclusion restrictions off of each of these. So if you take the first one and you guarantee there's no arrow, you get one thing. Causation, if you guarantee there's no arrow here, you get another thing, prediction. In fact, most things, of course, will have a mix of causation and prediction, and I think a lot of the wonderful work around high-dimensional data analysis and experimental design is actually exploiting that prediction, that we want some features of experiments that have predictive components and some features of experiments that have pure causal components. So this is the general case. From a derivative point of view, there's actually a very trivial notation here that has proven helpful for me. If I took the payoff function and simply took the total derivative, I end up with two terms. I take the partial with respect, I get the direct effect of x0, and I get the indirect effect. Why I'm doing this is you'll notice this is the prediction term. That is, the direct effect of our decision may depend on a y variable that we need some value of to gauge that, and this is the causation term. Importantly, for this way of thinking about this, what was valuable to me was to recognize these two terms and these two types of ways of thinking require fundamentally different empirical strategies. The things I would want under the prediction umbrella already you'll see is very good guarantees on y hat. My umbrella decision depends on having a very precise predictor of rain, of course. The causation distinction requires a very precise predictor of beta hat, precise and accurate, because it tells me something about the nature of changing the umbrella. Of course, we have very different guarantees on different statistical objects, but these two distinctions are, I think, super important. And if I were to caricature it, of course, things start to bleed into each other as more and more people working in machine learning or statistical learning get interested in causal inference. But to a first pass, if I take the simplest machine learning out of the box, I get a set of techniques for getting very good y hats. And if I take a good causal inference textbook, I get a set of techniques for getting good beta hats. And so this parity, almost like extreme distinction, helped me see, great, if I want to use these tools, the easiest way to kind of get the first piece of traction on them is to understand I now have tools to solve umbrella problems, because sure, there's now a lot of ways of trying to get beautiful coefficient inferences that we can trust. But having said that, the first order gist of this material is to get good y hats. So now I have a high-dimensional data analysis playbook that works without even relying on the second part. Let me focus on umbrella problems and let me find umbrella problems. So what I want to tell you is the outcome of this activity for the last year and a half, couple of years, is I wanted to answer questions such as, are there really umbrella problems, what we're calling prediction policy problems? What I mean by that is, are there problems in the world that policymakers are struggling with, which are important and consequential, and which are really umbrella problems? They have nothing to do with causality. Where, in fact, empirically, machine learning can add value. These are the questions I kind of wanted to get at. So let me give you an example policy problem, work through it in detail, and then we can work our way back. So in the United States, every year the police make over 12 million arrests. I know some of you are thinking, wow, that's a lot of data, which is probably not the right thing to think at this moment, but such is life. Now, when someone is arrested, what happens to them? So Richard is arrested for a low-level offense that I won't name. He goes before a Cambridge County judge. Do you want me to not bring this up, Richard? This is a public story, is that okay?
It's okay.
Yeah, okay, so he tells me he goes before a public judge. And the first thing the judge decides, this is not the judge that will decide whether Richard is guilty or not. This is actually a judge that will make, in 5 minutes, a pretty important decision for Richard. Where will Richard wait for trial? Now, this is a massive decision when you look at the 12 million arrests above it, because the release versus detain matters a tremendous amount to Richard and his crime-committing ilk. No, they're not crime-committing, crime-accused ilk, because pre-trial detention spells average about 2 to 3 months. That means between when you're arrested and when you have your trial, that's a long time. If Richard is sent home, that's fine. He's waiting at home for trial. It's not a pleasant experience. No one wants to sit around knowing what's going to happen, but he's at home. If he's put in jail, that's 2 to 3 months in jail. He's not been found guilty of anything. He's just sitting there waiting. It's one thing to call your employer and say, hey, sorry, I missed work yesterday. I'll be back tomorrow. It's another thing to call your employer and say, sorry, I missed work yesterday. I'll also be gone for the next 2 to 3 months, but I have a really good feeling about this. These are not the same sentences. It's consequential for the people involved. It's consequential for their families. It's also consequential for crime. After all, if we get someone in accused of a crime, we say, go wait at home, and they never show up again, or if they go on to commit a crime, we've basically just effectively let a crime happen that was entirely preventable on our parts. So what can we do about this? First, let's put ourselves in the judge's problem. The judge's decision whether to release or not, now of course they're actually deciding on a bail amount, but for the rest of this talk I'm going to abstract from that and simply just assume there's a release or not amount, is based on not just, you can ask the judge, you can look in the law. The law actually explicitly says this is what the judge needs to do. But the judges, they're doing what you might imagine them to do. They're deciding, when out on bail, will the defendant behave badly? Will they commit a crime? Will they reappear? That's it. What is the judge doing? They're making a prediction. This is an umbrella problem, 12 million umbrella problems being played out every day all around the country. And you'll notice it fits exactly what we've been talking about. The decision here is release. It affects the final things we care about, social costs. It doesn't affect the underlying crime risk to a first approximation. We can come back and think about it. But it simply affects whether that crime risk realizes itself on social costs. There are other things the judge can do. The judge can put a bracelet on you, for example, a GPS bracelet. That's an attempt to actually affect your probability of committing a crime because I'll be able to see where you are at all times. That's causation. But here, we're in a pure prediction world. So noteworthy things about this prediction, it matters. I hope you get a sense of that. The judge might have some advantages on this problem. For all of the data that I'm going to collect, right now we're not in a position where the judge, where we have put all the transcript of the conversation with the person into the data set, where we have put the demeanor. For example, Richard is sitting there with his hat on in front of me, the judge. What the hell is going on? Why isn't he more respectful? So the judge might have some advantages, see things the algorithm doesn't. But it's also note that the algorithm might have a leg up. The algorithm might have a leg up for 2 reasons. First, an area that I enjoy working in, behavioral science, we know people as decision makers, especially as predictors, can be faulty. So that's one leg up. The other leg up is even if you're in Cook County in Chicago, where there are a lot of people arrested. I don't know if there are a lot of crimes. There's a lot of people arrested. You get to see thousands of cases, tens of thousands of cases, but you will never get to see the millions of cases that an algorithm can learn from. So we have a data advantage, and we have sort of a lack of human bias advantage. We have a disadvantage, which is we're not observing everything in the situation. So the question that comes to us is, this matters. So what do we do? I hope you realize that for me, the most important thing was the realization that I'm putting it matters twice, because for all of the policy things that I've worked on, I was struck by the fact that here's an umbrella problem. I spent a lot of time focusing on causation, but here is a pure prediction problem with as much importance and consequence as any causal problem that I had worked on. So what can we do about it? So what we did is we have now done this on many different data sets. I'll show you the results from 2 of them, but the results seem to be pretty qualitatively similar. We went and got a bunch of data. The data all has the following structure. It's variables where we know here is a person, here is the history of the person at the time of arrest, and here is the outcome of what eventually happened to them. Were they released? And if they were released, did they commit a crime? Did they fail to appear? Did they commit some other crime? Did they commit some other violent crime? So what we basically have is a massive data set of the thing to be predicted, the y variable, and a bunch of x's that the judge saw. Of course, the judge saw many more x's, but a bunch of x's the judge saw. The variables involved in this data set are shockingly uninteresting. They are just the kind of things you might have imagined you would get in a purely administrative data set. There is, if you've read any paper with interesting right-hand side data, this is not one of them. If you look at the data, there are things like, have you ever had a previous conviction? What is your active arrest? It's nothing, there is not a variable here that I could ever hope to go back to the judge and say, did you know this variable mattered? I mean, of course all these variables matter. The question is in what combination and what degree. So we then took this and simply ran a few predictors on them. I wrote estimators, but I won't go into them. But for example, we tried 3 things: boosted decision trees, random forests. We did some hierarchical modeling to account for the fact that the data comes from separate counties and years, and you might want a separate model for each county year cell than one universal model. We can get into details on that. And then, of course, I'm going to show you all the results on a holdout set where none of this was polluting it. What this produces for us is the crime prediction rule. It gives the algorithm a y-hat, a prediction of, faced with this person, what is my best guess of the probability that they're going to commit a crime? How am I going to evaluate this? I think this is one minor distinction. Normally, we might evaluate this with some AUC or ROC. What makes it interesting to work on such a concrete decision problem is ROCs are not very important here. There's a much more intuitive curve that we want to produce, and that's what I'm going to show for you, which is take everybody, rank order them by probability of crime, and have the algorithm create from its prediction a release rule. Release, if I want to release 1% of the people, release the riskiest one. If I'm going to release 2%, release the riskiest 2%. So now I have on here the x-axis, the release rate of the algorithm. And on the y-axis, I say, if I release these people, what happens? So that allows me to generate a curve that allows me to say, if I release 1% of people, 2%, 60%, 80%, what happens? So now I have a trade-off between release rates and crime rates. I feel like all of economics is about finding some trade-off or other. And to do this, you quickly encounter an enormous problem, which may be already apparent to you guys. Here's the problem. The algorithm decides, oh, great. These are at 50% release rate, these are the 10,000 people I would release. Then I say, great, let's evaluate your performance. Oh, wait, there's a problem. I can evaluate how well you did in this holdout set on the people the judge released. But how on earth will I evaluate how you did on the people the judge jailed? So even though this is a pure prediction problem, there's like sort of a fundamental empirical barrier we've now encountered. I'm going to tell you this because this empirical barrier is, I think, not small. I actually think it's enormous, and I think it's canonical. In every problem we've worked at, we encounter this problem. You could call this almost a missing labels problem. I don't have labels for everybody. That misses the point, because to call it a missing labels problem suggests it's some randomly missing labels. It's selective labels. The people for whom we are missing labels are not random. They are the people for whom the judge felt the labels would be particularly high. It's actually a selectively deleted data set. And I'm trying to evaluate myself against this person, so in a way, what do I do? Because these are the people for whom the judge had some belief. So I'm going to start with something very simple just so we can move forward. I think this problem is very big, but the simple thing I'm going to do is I'm simply going to impute crime rates for these people using the release set, using their observables, and impute. This means that I need to be a little bit more careful. I can't have the algorithm scoring itself, so I'm going to have a train set, an impute set, a separate set simply for imputation that a separate algorithm does, and then apply the imputer and the predictor onto a holdout set. This is very problematic because, keep in mind, I have now brushed under the rug one of the sources of advantage the judge may have. But I want to kind of put that aside for a second. I'm definitely coming back. It can create a problem if those released are different, not just on observables, but on unobservables. As I said, the judge sees a lot of things that I don't. That is obvious when you look at my data set. I'm going to return to this later. So let me show you the crime rate, release rate we get with imputation. This is the trade-off. This trade-off requires us to evaluate it for something. I could look at the area under this curve or something, but that gets very hard. So how do we create an apples-to-apples comparison? The apples-to-apples comparison is to observe, the judge has a release rate that is 61%. Why don't we simply ask, what if I released 61%? I get about a 13.8% crime rate. The judge gets about an 18.7% crime rate. It's an enormous drop in crime rates just moving to the algorithm. Well, another way to see how large this is, first of all, if someone said to you, I can drop the crime rate by 4 percentage points simply by jimmying the prediction rule, that's shocking. There's no causal effect that's that big. But here's another way to think about it. Suppose I went in the other direction. The judge is seemingly happy with an 18.7% crime rate. Why don't I go to the right and ask, how many people could I release? I could actually release 78% of people. It's as if I could cut prison populations by 40% tomorrow and have the same damn crime rate. That's a sense in which the extent of misprediction is enormous here. With these scales, it looks like, oh, it's a small move up. When you put it back into socially meaningful numbers, it's an enormous move up. Of course, so this is by way of saying there is an umbrella problem. It does look like machine learning is incredibly valuable, as you might have imagined. And in other data sets, we actually get reductions of more than a half of prison populations simply by just switching to this rule. But of course, all this could be a mirage. The mirage could be driven by the fact that we have this selective labels problem. We are, in fact, created a situation to artificially make the algorithm look very good. The problem is, of course, of unobservables. To understand it, let's get through a very specific thing. What would be the most extreme case? Let's suppose the judge sees something about one category of people. So for all young people, the judge sees a mark on their forehead that determines whether they're going to commit a crime or not, perfectly. So the judge looks at it and simply just releases the people without the mark and keeps the people with the mark in jail. What that means is that in the release set, the young have zero risk, because those are the only people who are being released. As a result, if we impute, it's favoring an algorithm that releases all young people. Because I'm telling it, hey, look, I've looked in the data, young people don't commit any crimes. You're releasing everybody? Great. But it's an enormous bias in our imputation procedure, because young people don't have zero risk. Young people have whatever risk young people have. I have no way of assessing it in this data. And if we don't fix this, we are fooling ourselves. So how do we fix it? So to fix it, I want to walk you through my attempt to do graphics, which is not going to be pretty. So let's start with a little representation of what the human is doing. They're taking the set of people, coloring some people and saying these people are released, these people are jailed. The machine is taking the same set of people, coloring some people and not coloring others. So we've got these two sets. Obviously, they are not releasing the same people, otherwise we'd have no way to compare them. So I put one vertically, one horizontally. Then what I'm going to do is to think of the intersection of these two sets. And I'm going to look at the fact that, notice that what I have is on the diagonals, the algorithmic rule and the machine and the human rule agree. So there's really nothing to be done here. It's on the off-diagonal elements where there is a big problem. And let's walk it through a little carefully. Here, the machine says jail the person, but the judge releases them. But we have the label. There's no problem on that side. the entire problem arises here. The machine says, release them, but there's somebody the judge jailed. This is a way of understanding that selective labels is not a generic problem that applies broadly. It applies in a purely one-sided manner. It applies when the algorithm releases and the judge does not release. Once we understand the nature of the one-sidedness, you can start to see how we might build a solution to this. Releasing a jailed defendant doesn't produce a problem for measuring performance. It's jailing a released defendant that does. This asymmetry suggests the problem was not with the original prediction technique. The problem was with how we went about evaluating the y-hat predictors we got. We used them to simulate a release rule that was entirely unconstrained and engaged in both sets of operations. So this is not with the rule, it's with how we're using it. Just to walk through it, let's do something different with that rule. Let's take the set of released people by the judge and ask the question, great, with the released people, let me rank order the people you released ex ante. So I'm sitting next to you as you're releasing people. I say, you know what might be interesting to you? This is my best guess of that person that you're about to release's crime rate. So we can do that in the release set, no imputation, actually work out the labels in the holdout set, and actually ask how well does my prediction in the release set do? This is the distribution in the release set where I put the percentile. We call this quasi-contraction for reasons that will be clear in a second. And what you see is that the predictably riskiest population, that is the people who could have said ex ante, have about 55% risk for this particular model. That means, is the judge really knowingly saying, Richard, you can go home when he's got a greater than 50%? No judge is actually would actually choose to release somebody if they knew there was a 55% problem. This already tells you that there must be a big bias going on, because this we can evaluate, and we can see there's a big gap between the people the judge is releasing and the people we would have predicted, and that gap results in pretty material differences. So we'd like to be able to go from this type of insight. I'm calling this quasi-contraction because I'm basically contracting here the released set. That's the operation that's allowed. I'm taking the released people and making it smaller. How do we turn this into a full estimator? The way we turn this into a full estimator is to observe that in almost all the data sets we have multiple judges with similar caseloads and differing leniencies. So the strategy is to use the most lenient judge and contract from there. So here's what I'm going to do. Take the 90% released judge. Now, normally, I would have used that judge and simply just picked the people I'm going to release if I wanted to get to an 80% release rate. But that's what led to the selective labels problem. But suppose I wanted to get an 80% release rule. Let me contract from the 90% judge, obey the people they jailed, and pick another 10% so that I ended up with this stripes being 80%. This is a contraction from 90 to 80, but that is entirely evaluatable. Notice how this contrasts with imputation. Imputation willy-nilly just picks a bunch of people. So it's a constrained evaluation of the rule. It's in some sense handicapping the prediction rule because I'm not letting it do whatever it wants for purposes of evaluating it, but it'll give us a lower bound on its abilities and its qualities. So just so you understand, the imputation procedure simply just went from this 90% and was forced to impute. This contraction procedure, we can measure its performance everywhere. So that's the nature of the contraction exerciser. Now we're going to take the 90% judge, contract, and come up with an 80% rule, which we then will compare to an 80% judge. And working in this way, we can contract our way down judge by judge by judge. That's the essence of the contraction estimator. And the contraction estimator requires that judges have similar cases, something like random assignment. But notice random assignment is not really playing the role that it does in causal inference here. For example, if you told me what's my dream data set, it's not random assignment to release. It's a judge who mailed it in and released everybody. That would be my ideal data set, because it's selective labels in one direction. I actually just want nothingness, not random assignment. It doesn't require that judges have similar rankings, because I'm simply just using the 90% judge as a data generating process, not as any sort of thing. But it does give us performance of a different rule. It's kind of the human constrained machine rule. But we'll have to look at that. What I'm now going to do is I'm going to apply contraction to a data set and compare it actually to my original imputation procedure, because that will prove enlightening. This is the performance of the judges themselves, the top layer. And these are different bins of judges according to the release rate. And this is the imputation procedure, and this is the contraction procedure. What's shocking is how close contraction is to imputation. It suggests selective labels is there, but it's a minor effect if at all possible. which to me was super enlightening because in this case it's not a problem. I can talk about other cases where we found it to be generally a problem. But it's shocking that it's in this case it's not a problem because the judge sees so much that we don't see. So maybe this tells us something not just about a prediction rule, but about the nature of the behavioral science going on. That is, if we were to ask the question, why do we beat the judges? And you combine it with what I just said, I would have said, the judges see more than we do. So shouldn't they be doing much better? Perhaps we could flip the question on the head and say, perhaps that is the problem. Perhaps the judge sees more than we do. With machine predictions, it's rare that simply giving more X variables is going to make the algorithm significantly worse. I mean, we gave it noise, it's going to introduce some regularization problems. But if we gave it signal, by and large, that's going to be helpful. But humans don't work that way. Humans can see a lot of noise and treat it as signal, and it can induce a lot of biases. An example could be my fixation on Richard's hat, thinking that he's being rude by not taking it off, could be entirely noise. It has nothing to do with whether Richard's going to commit a crime. It has only to do with his hat. So that gives us a way to potentially even, not just in this case, produce a better predictor, but understand the behavioral science of the judge. So how could we understand this? Suppose I were to compare the judge to another prediction. Think about what it says here. This inference that I'm making suggests that the problem of the judge is the use of the variables I don't see, which suggests maybe I could form a version of the judge that does not use those unobservables. How would I do that? Let me pose a new prediction problem. The new prediction problem is take the x's and predict not crime, but predict the judge's behavior. So now I have a j-hat. That j-hat is an interesting object. The j-hat is my projection of the judge's complex rule onto the space of observables. And I will now compare j-hat to j. I will ask, how well does this simulator of the judge, this crude simulator, there's predictive power, but it is far from perfect, do relative to the judge themselves? So here's what I've done. I do a weighted rule where I weight the judge on the left-hand side. So I weight gamma j plus 1 minus gamma j hat, and I vary gamma. If I move all the way to gamma of 1, I end up with the predicted judge. If I put gamma of 0, I'm at the judge, and I just vary gamma. And I ask, how does this set of rules do in this data set? And what I find is that actually we always do better moving from the judge to the predicted judge. It's kind of funny because this is a form of bootstrapping in which I say, forget what you are going to do. I'm going to say, what would I predict you're going to do? And my prediction of you is better than you. It's kind of shocking in its own way. But yet, the behavioral science, actually, this is about 35% of the gap between the judge and the algorithm is covered just by j-hat. That is, not trying to put more signal in, but just taking the signal that's already there. Now, what is this saying? This is because it must be that all these unobservables that the judge is using may have signal, but the judge's tendencies to overweight the signal, to look into Richard's eyes and see his soul, that must be playing too big of a role. And that, in fact. So to me, this little exercise turns out, I believe, to be kind of encapsulate the entire prediction policy problem. So I'm going to take the last 9 minutes, 8 minutes that I have, and I'm simply just going to tell you about that whole category of work. I think Bail is the tip of the iceberg. I think policy problems like this are ubiquitous. In fact, in every domain where social scientists are working on causal inference, there is an adjacent prediction problem. They all have these features. Let me give you some other examples. A lot of people work on health economics, and they talk about low-value care. They say, if I look at doctors and I was to go into a doctor and complain of chest pain, the doctor would say, oh, you have chest pain. They might, at that point, give me a stress test. They might, at that point, catheterize me. These are all very expensive procedures. What we know in the United States is that these type of medical testing decisions have very low value. So the causal question there is, how do we get doctors to do less of them? The prediction question is, this doctor is like the judge. They are making an implicit prediction. They are saying, given everything I see about you, is this chest pain indicative of a potential heart attack? Or is this chest pain indicative of the fact that you are having a bad meal yesterday and it is merely indigestion because people confuse the chest with lots of things? The doctor is a predictor. So in some sense, you can naturally ask the question, instead of trying to change their behavior through incentives, could you change their behavior simply through better predictions, much like we did here? And the early work seems to suggest that a ton of low-value care, the things that health economists obsess about, are actually just about misprediction by the doctor. That the doctor's ranking is wrong, not where they draw the line of how much testing they ought to do. Another case is what we're calling retail crystal balls. Think about how shocking it is that if you were to get unemployed tomorrow, you would be in this bewildering mess where you'd have to make a ton of consequential decisions yourself, where you'd have to say, will my spouse start looking for work because we might need the money? Should I sell the house? Should we move to a smaller house? Should I take a loan? Should I cut back on consumption? Should we move kids out of whatever? All these decisions are all based on a prediction. How long will my unemployment spell be? What a weird world we live in that we leave all those decisions that are implicit predictions to people themselves without giving them any of the crystal balls that we could produce. We have all of the data in the state unemployment systems to give that number back to people, to say to people, here's our best guess of your number. Here's another one. There is an enormous amount of work built on recommender systems, which are merely predictions of what we think you'd like. You know what's funny? If I want to figure out what movie I want to watch tonight, which is how I'm going to spend 2 hours of my time, there are really good recommender systems. If I want to figure out what major I'm going to take and I will do well in, given my things, and I'm a community college student, there's no really good recommender system, even though we have all of that data, and that's how I'm going to spend 2 years of my time, 4 years of my time. If I want to decide what industries, given that I'm unemployed, should I be searching in, where will my resume have a highest chance of a callback? Well, good luck with that. Of course, people are building these things, but it gives you a sense that exactly the things that social scientists are focusing on, there is a big thing. So that's to say that we could spend time on causal inference, and we must, but there are a set of micro predictions, and that's the key here. Predictions made en masse, 12 million arrests, 100 million people searching for a job, that are all these micro predictions. I don't believe this is just a matter of technology transfer. That is, great, there is a field out there, it's producing statistical tools, we just need to use them. Of course, I think the first order gain is the use of this, but it's that once we start using these tools into a decision framework, you start to realize there are a bunch of questions which we may have partial answers to, but where we really need much more answers. The first of these questions I've already shown you, the selective labels problem. The selective labels problem is not an oddity with respect to bail. Let me tell you why it's a general problem. If you simply just took bail and just said, I came up with a predictor, you would never encounter this. It happens when you say, I'm interested in the decision. I'm interested in how the prediction generates a decision, and instead of coming up with the predictive quality of y hat, I would like the simulated decision from y hat. It happens whenever that happens because we are in a situation where we are interested in an algorithmic sort of decision aid, but the data is being generated by a process where there's already a set of decisions happening. In this case, my data comes from a decision process. So as a result, I have prediction that was already there, decision, treatment. So selective labels in this case is because the decision was jail. In the medical case, I want to predict whether there's going to be a discovery of a heart attack and a catheterization procedure. Guess who I have data for? The people the doctor chose to catheterize. So selective labels of this type shows up everywhere. The second type of thing which we have good things for, and I suspect there's very little to add because this has already been covered in spam detection, is that unlike a lot of problems such as face detection, most social science problems have a feedback loop in which the data responds to the prediction function. If I start using a set of variables to predict whether you'll get bail, guess what people might do? They might start gaming those rules. Of course, we know this. We know this in the spam detection literature. But that logic, I think, will loom large here. The other thing that happens here is constraints on input. This is perhaps the most important one. Unlike in most problems where we're allowed to use anything we want, in this case, take the Bayes example, we have variables we're not allowed to use. I didn't use them, but race and gender are not legal to use, nor would we want them to be used by the Bayes predictor. The question is, how do we do prediction in the presence of these prohibited variables? I think this is an important question. And it's an important question because I could tell you we don't use them, but what I can't tell you is that enough? How do I know that my algorithm is not being racist behind my back? This is not simply a question for the machine learning side. This is a question at the deepest level at the legal side. Because we only have definitions of racism, legal definitions of racism, in a world where humans are making predictions. It's very hard for us to know how we're going to start redefining the notions, the legal doctrines of racism in this context. So I have to take constraints on inputs. The final thing I'm going to talk about in my 1 minute left is what I want to call omitted payoff bias. This is a pretty big problem. To walk you through this, let me show you a problem that shows up in the causal inference world, which everybody is familiar with. This is the causal graph. Suppose there's some unobservable variable z. There's a covariance between z's and the x's. These unobservable variables will create biases on the coefficients. This is omitted variable bias. It's very familiar to everybody. What I want to observe is omitted variable bias in the world of prediction is not a bug. It's a feature. That's awesome. You mean there are some unobservables that aren't in my data set, but that my x's covary with? So for the purposes of prediction, I get even more signal from my x's than I thought? Good stuff. But what is a bug is actually, since this is the object we care about, suppose there's a w variable and an unobserved w variable that feeds into payoffs. And that w covaries with my x's. This covariance with w is now a problem, and actually a major problem. Just so you understand, let's walk through what would be an omitted payoff bias in Bayes. The omitted payoff bias in Bayes would be if the judge is not simply assessing guilt on this crime. The judge is not assessing guilt on this crime. But suppose the judge wanted to pay attention to something other than crime risk. For example, the judge says, yes, I care about crime risk. I also care about families. So if someone has a child, my preferences involve releasing them at the same crime rate. Does that make sense to everybody? So the W here would be having a child, which I never see. I go into the data and say, you're only maximizing this Y variable. I've rank ordered people. Look at all the gains I can get by putting these people in jail. And you say, that's not a gain from my payoff function. That's simply a gain in the Y space. I just explained to you I also care about kids, which you don't measure. Now, in this case, it doesn't happen. Why? Because with bail, judges actually do just care about these things. It could happen with family, so happens it doesn't. Let me show you an adjacent thing where it's a huge issue and why you couldn't even get this project off the ground. With sentencing, you could have the same issue. You could say, why not predict what the person's probability of crime in the future will be, blah, blah. But sentencing decisions aren't just implicit predictions of future crime. They have a huge number of other omitted payoffs, retributive justice, a variety of other things. So these two problems adjacent to each other, crime probabilities, release decisions, and sentencing decisions will operate very differently, even though the prediction task looks the same, simply because of omitted payoff bias. Okay, this is my concluding slide. As I said, these problems are ubiquitous. I think the reason that this is only the tip of the iceberg is that the numbers we're discovering in the Bayes example are huge relative to causal inference work. And I think that comes from behavioral science. We know that in the behavioral science world that people are not great predictors, that we're not good at taking large volumes of data. But as I've shown you, we are leaving people with tons of umbrella problems that are consequential in exactly the place we think they shouldn't do. As I've said, it's not just technology transfer. Randomized control trials, I think, have revolutionized social policy in the last 20 years. That, I think, was a move of causation into this world. And I believe that in the narrow world I live in of policy that has consequences for all of us, I think the prediction will be the next revolution when properly applied, because there are so many of these problems. But I don't believe that this activity is going to happen in and of itself. I think that there's a huge amount of work needed. And I think that hopefully I've convinced you that there's an exciting area for people to work on. So let me stop there. Thank you.